Hi everyone! In this video we'll take a look at how to deal with significant figures, or sig figs, following calculations of multiplication and division. Constantly having to keep track of sig figs is one of those things that can seem annoying. However, it is definitely not busy work. When we take measurements or use them in calculations, it is really important that we retain the precision of those measurements. In other words, we don't want to misrepresent the precision or reproducibility of our measured values or the calculated result. This is why dealing with sig figs is such a big deal. Now, while this video focuses on keeping track of sig figs during calculations, we can't do this unless we understand how to count sig figs and how to identify number of places in a measured value. Here's a brief review of the rules. Exact numbers never count when they're part of any calculation. We just ignore them. When we're counting how many sig figs we have within a measured value, leading zeros never count. And trailing zeros only count if there's a decimal point shown. It's the zeros where most mistakes are made, so it's worth remembering these 2 points. And finally, all other numbers count. If we have to determine places, we assess which digits are significant in the value and locate the one that is furthest to the right, then label that position. You'll see here that I will count decimal places when the final sig fig is to the right of the decimal point, and use the formal term for place value if the final sig fig is to the left of the decimal point. I think this makes things easier. In a calculation, we'll identify the value having the fewest places as the one where its final sig fig is the furthest to the left. For calculations involving any combination of multiplication and or division, we want the fewest number of sig figs. Our strategy is to count sig figs and label how many there are in each value. If the value is exact, we'll note the sig figs as exact so we remember to ignore those. Then round the calculated result to the fewest number of sig figs coming from these values. In our first example, we will round this calculation to the proper number of sig figs, and we're told in the problem that the 8.314 is exact. So we'll count how many sig figs are in each value, then we'll do the calculation and round the result to that fewest number. Our first value has 3 sig figs. That one is pretty straightforward. There aren't any leading or trailing zeros that we have to deal with. In our second value, we have a leading zero, which we'll ignore, and we do have 2 trailing zeros, which we count because there's a decimal point. So our second value has 4 sig figs. And our final value, the 8.314, we were told was exact, so actually write that down. Write down that it's exact, because that way, after we do the calculation, we come back to check how many sig figs we need, then it's right there. We don't even have to think again about it. So doing the math, 1.01 times 0.3400 times 8.314, rounded to 3 sig figs, that was our fewest number out of the values that we had, gives us 2.86. Our next example is a division. We have the same goal. We're going to do the calculation and round to the proper number of sig figs. Here, we're not told that any value is exact, and so we will count the sig figs in both values that we have. So in the numerator, we do have some leading zeros, which we ignore, and that means we have 3 sig figs in that value. In the denominator, we also have a leading zero, which we ignore, and we have 2 sig figs in that value. So when we do the calculation, we're going to round to the fewest number of sig figs, and so our result will have 2 sig figs. Doing the math, 0.0551 divided by 0.42, rounded to 2 sig figs, gives us 0.13.